All right, so welcome to our next presentation in our series of training seminars for how to use HAL and how to implement machine learning methods on HAL. Today, I'm very happy to introduce William Eustis, who is an undergraduate student here, actually. He has been with our Center for AI Innovation since this summer, and actually one of his specialties turned out to be data loaders. And so he was very instrumental in one of the projects that we had this summer. And so he is now going to present us how to build data loaders for PyTorch. So William, let's take it from here.
Sounds good. Welcome everyone. So today I'll be discussing how to build data loaders in PyTorch. And so we'll go ahead and just get started. So first, a little introduction about me. My name is William Eustis. As mentioned, I'm currently an undergrad student. I'm finishing up my my Bachelor of Science in Computer Engineering. I work a lot in computer vision and in hardware accelerators, and I work with Professors Gruev and Schwing, as well as with Professor Kidritenko. Yeah, so we'll go ahead and get started with the actual kind of content. Okay, so the big picture behind data loaders in PyTorch are kind of as the name suggests. So data loaders are the way that we're going to load our data from whatever storage medium we have them in, a hard drive, an SSD ideally, into whatever device's storage is necessary. So if you're training on the CPU, that'll be the RAM. And if you're training on the GPU, eventually that'll be VRAM. So data loaders can also perform augmentations for your images. And in fact, one of the large strengths of data loaders that we'll see in an efficient data loader is that it can do so asynchronously. So your single process won't have to wait for these augmentations to be performed in order to start actually computing, the loss function and performing a forward pass on that on some other data. And in many cases, loading your data is actually a major bottleneck of a training script. So if you have, maybe very large data, if you're doing something like 3D scans, or you have maybe very, very many different files, this can very quickly kind of overload your system's I/O, and it can become the major bottleneck to the point where your GPU can keep up with however much data it's getting, but it can't quite reach full utilization because you just can't give it enough data fast enough. So what we'll be discussing today is, first of all, just the basics of how do I create a data set and data loader in PyTorch? And then eventually, how can I optimize this in order to load as quickly as possible and for my models to train efficiently? If you want to follow along, I believe the Jupyter notebook is linked in chat, or the GitHub that includes it. You can upload that to Colab, which should have all of the necessary packages installed. You can have it on your local machine. You could have it on HAL. Whatever is really necessary for you, it should work. Okay, so first, let's talk about the data set. So this is kind of the first step when you're creating data loaders and data sets in PyTorch, is to create what we call a data set. This is a class within PyTorch, and let's explore how we actually create it. Great. Okay, so step one, of course, is the imports. The most important one here is the torch.utils data set. This, of course, is importing our data set, or importing the torch data set class that we're about to extend off of. Okay, so the way we can do this is just begin by creating some class, and we'll call this my data set. And at first, I'll just work in this sandbox, and eventually I'll swap over to the main code and show you the results there. And this is going to import or inherit the dataset class that's part of PyTorch. And there's really three major functions for a dataset, or for a map style dataset. We'll look at another type eventually, but the major ones everyone's going to be working with is these map styles. And those three functions is the init function. Oh, sure. Yeah, I can zoom in a lot. My mistake. Sorry, I have a nice big monitor, so sometimes I don't have to worry about that. Is this better? Wonderful. Okay, so the init function. One moment. Oh, I see what's happening here. Okay. We have the length function. We have the get item function. And of course, these are all going to take self because they're part of some class. And let's really explore what each of these do. So the init function for some data set is just going to set up whatever is necessary. Very often, what this will mean is we're going to provide it with some path, and it's going to load this data in some way, or preload it, or do something in order for these later functions to be able to access this information as well. In particular, in the example that we'll be looking at, let me make sure I'm following it. We also use this Blob Library, which just allows us to kind of view different files. And what we say is glob.glob path. And so what this is saying is give me a list of all of the files in this path. And so what we'll do is we'll call my data set with a path to all of the images that we'd like to load our data on. And then additionally, in this case, just a useful thing that we'll use is end classes. Specifically, what we'll see in a second is the data set that this Jupyter notebook that I made has 64 classes, each one with, I believe, 24 examples. Normally it's 600, but we actually skip every 25th item just because we don't necessarily care about accuracy. In this case, we just care about creating these data loaders. And that'll be useful for actually creating this data loader itself. Okay, great. So the length function is pretty straightforward. We have exactly one image for each file. And so we can just say, return length self.path. Self.path, of course, if we remember, is going to be a list of all of the files, each of which is going to be an image. And then for the get item, in this specific case, we can see here when we're creating this data set, I've actually saved the image's class information in the name itself. And so we can break it down there. But in other cases, if you have maybe a CSV, what you can do is load the CSV in the init and select maybe a certain row to get the class there. Really anything that is necessary. But the big idea of the get item function is just to load that item in and eventually return it. So I'll just copy what I have here to save a little bit of time and break down what's happening. So the get item function also takes the index of the item we want to get. PyTorch is yelling at me for spacing, or Python. And so first we're going to get the name of that file just by taking the index of self.files. Then we'll load this image in using the Torch Vision IO read image. Of course, there's a million different ways to load images in, or if you're not working with images, there's a million different ways to load whatever type of data you are using in. And we'll actually explore some of these in a little bit. And we'll just make sure it's a float. We'll extract this class ID out of the name of the file. Once again, if you're storing your class labels in a different way, maybe in some case we have self.labels equals, some read CSV here. And we say something like self.labels of IDX. Many different ways. Personally, I like to store it in the class name, so that's kind of useful. Additionally, maybe a very common format is having data, and then, for example, this class is cat, this class is dog, and then within this we have like 000.jpg. So this sort of format. And in this case, it's actually very similar. Basically the only difference is we would split on the slash and get the file name, or the folder name rather. Okay, so this will work for our implementation, but we need to remember that this class ID is going to be some integer, right? The class ID 0 to C. I believe C is in the range 0 to 64. There's 64 different classes, so it's either 0 to 63. But we want to actually convert this into a one-hot encoding because that's going to be a little bit more helpful for our training script. And so what we can do is just do torch.I, which is the identity matrix. And then we'll just take the index of the exact class that we want. This is just one way to do it. There's kind of many different ways. The important thing that I want to outline here is you can kind of post-process your label as well. So feel free to do that. And then we'll return the image as well as the label for that image. Great. Okay. So what we can see is we'll actually implement this. So we'll pass it the data path, and we'll just select some random example. So we'll say data set of 42 has this size. Of course, in PyTorch, we have channels first. So 244 by 244, red, green, blue. And we'll just show this image using Matplotlib. And we can see it's a picture of corn. And then we'll just iterate through our data set until we find another example of this class that is not the same image. And we'll show this one as well. And we can see it's a second picture of corn. So maybe these are from the Morrow plots, fingers crossed, but who knows? Wonderful. So that's really, we've kind of done it already, is we've created some data set and in a way a data loader. Of course, it's not quite efficient to iterate over this data set object manually. And so instead, we will use this data loader class. And so let's explore some of the parameters that we'll pass to this data loader class. This is a class that exists already in PyTorch, so we don't have to worry about implementing it manually. And in fact, it's extremely useful because it allows us to asynchronously load this data with different Python processes from our hard drive or our SSD straight into RAM, where it can then be transferred often to the GPU quite efficiently. So the parameters, the most important one, of course, is going to be our data set class. So we'll pass that in, and then we'll explore some of these parameters in just a moment. But, kind of key ones: batch size, how many images are we, or how many samples from our data set are we collecting at once? Are we shuffling our data set? We can have custom samplers from our data set, custom batch samplers, number of workers, being how many different workers are kind of loading this data in parallel. But for now, for our first implementation, let's just say batch size equals 1. And of course, we want to shuffle our data. Okay, and we'll run this. And what we see is it takes about, we'll say 550 milliseconds to run through our entire data set, which is not bad at all. So this is, quite efficient, I'd say. And let's actually do a quick training script and see how long that takes overall. So we'll use ResNet 18. We'll change the model head in order to be the correct shape. We'll create our loss function in our optimizer. And then we'll just train our model for 4 epochs. Nothing too crazy happening here. We're moving our data onto the GPU. We're performing a forward pass, calculating our loss, optimizing our model, and also additionally printing the loss every once in a while. So we can see it trained successfully, and it takes 1 minute and 4 seconds. So, nothing awful. It's not too bad. And we can see, the performance of the model is okay. Of course, this is quite kind of a difficult problem, and we're not letting it train for very long, so we don't expect amazing results. But let's actually explore some of these parameters in some more depth. Okay, and really this is something that I encourage all of you to do. So once you've created your data set, and we'll look at more examples of data sets for different tasks later, but once you've created your data set, one of the first things you should do is start to optimize your data loader. And what that's going to look like is, we don't exactly do a grid search. We kind of do these one by one. But, if you need to do a grid search across these different parameters to find whatever is best, I highly encourage you to do so. So first, we'll just take a peek at batch size. And we can see that generally a batch size around the range 2 to the 3 to 2 to the 4 works best. Much larger batch sizes like 2 to the 6 to 2 to the 8 can work, but sometimes they're a little bit noisy. So we'll set 2 to the 3 as our batch size. And let's also evaluate how many workers we have at once. So what this means is how many different Python processes are being spawned in order to load the data from the hard drive or the SSD onto or into RAM. Eventually that, data in RAM is going to be moved into the GPU. Okay, so we can see here that we load this data in, and generally any number of workers kind of greater than 0 is going to be a little bit more efficient. So greater than 0 workers obviously means it's the same process. We're not doing anything incredibly intensive, so there's not a huge delay, but any number of workers kind of greater works. Again, this varies widely depending on your machine and depending on your data set. So I encourage you, do this on your own. For this specific data set and this specific machine, it seems like there's not a huge benefit in having additional workers. Okay, additionally, we can check this prefetch factor. This says if we have some number of workers, let's preload, n images into RAM so that when we start the next batch, we already have it ready. And we can see once again, there's a little bit of a benefit around 2, and then it sort of starts to drop off. One thing to keep in mind with all of these parameters is there's always going to be a trade-off. With more workers, you're going to have more processes running and more input output from your system. So you might say, if I have a CPU with 64 cores, can I just have, 128 workers or something? The answer is no, because, at the end of the day, your system is limited by how much input output it can have. And often spawning workers is actually expensive in and of itself. And so evaluate it, if it is faster for your specific case, that's wonderful. But often we see that with very high worker counts, it starts to slow down. Additionally, if you have 128 workers and your prefetch factor is, we'll say 4, that means each worker is prefetching 4 different items from your data set. And if each item from your data set is each one's preloading that many batches from your data set. So if each data set example is very large and your batch size is very large, and your number of workers is large and your prefetch factor is large, you can very quickly start to run out of memory. In fact, quite more rapidly than you'd think, just since there's so many things being multiplied together. So once again, we can evaluate the prefetch factor. We see that it works a little bit better. And additionally, we have pin memory. What pin memory does is it aligns the memory that we're loading into RAM into a certain spot with paging, in order to more efficiently move that onto the GPU once it's requested. And we see in this specific case, it actually doesn't make a significant difference. In certain cases, people have claimed that pin memory is slower or faster. So this is just another thing that you should evaluate. Generally, though, pin memory is going to be faster, I believe, if you're working on the GPU at least. Wonderful. Okay, so we've now tuned our parameters a little bit, our batch size, our number of workers, our prefetch factor, pin memory, all that. And so let's do the exact same training script. But the only difference now is our data loader is a little bit more efficient. Okay, so previously, our training script took, I believe, 1 minute and 4 seconds. And so now that we've optimized all these values, our training script takes 8 seconds. Which is quite a significant difference. We're training on the same number. I mean, obviously our batch size is much larger, but our model is looking at the same number of images. And so this is maybe quite effective. We even see that it gets a little bit lower loss, I believe 3.6 versus something like 4.2. But that's probably more due to the fact that this above model is training stochastically, doing backprop after each item while the other one is doing, batch. So that's probably the reason for that. Nonetheless, it's about 10 times faster. I mean, not quite, but just about. So it really is quite important optimizing your data loaders, but we're not quite done. So right now we're just loading these images in from memory, but a very common approach is including data augmentations as well. So in fact, what happens if we store it in a different file type? Right now we're loading JPEGs. What happens if we include data augmentation? And, if our data set is small enough, which in this specific case it is, can we preload a lot of this into memory? And the answer to all of these is of course, yes, we can do this. And in fact, it often, improves performance in some way or another. Okay, so specifically, let's look at how to add augmentations to our data set first. The only adjustments we'll need to make is first creating this self.augments object or transformation composition, usually within Init. Because this is something that's constant, we don't need to regenerate it every time, so we can just kind of keep track of it. There's other ways to do this as well. I won't get too deep into the Torch Vision transforms, but there's a lot, and I encourage you, in your specific case, look into some of these, see if it works for your case, and maybe it's good, maybe it's bad. So these are just some random augmentations that I chose that are obviously going to maintain kind of the structure of the image. We randomly flip, we normalize the colors, we randomly crop and resize, we change the brightness and saturation and contrast a little bit, and we randomly rotate. Okay, the length stays the exact same. And the only difference now is we also need to call this self.augments on the image, and this will augment the image, which will eventually get passed back. Wonderful. So let's try the exact same training script. The only difference now is we're now using the augmentations as well. Okay, so now it's taking 28 seconds, just about. So it has slowed down a considerable amount, but you could argue that this is worth it because we've effectively increased our data set by a large margin, right? We have much more variance in our data set. And even, I might add, for this specific case, we're kind of in the few shot range. We only have a couple samples per class. This could be, widely effective if we let it train for longer, which we don't. So, sometimes augmentations are necessary. And so we need to be able to kind of add them, even if that's going to mean slowing down our model. On the bright side, most of these are happening asynchronously. So if we were to, example, change this to 0 workers once again, having it all run on the same process, I didn't benchmark it, but it would be considerably longer than 1 minute, probably in the 2-minute range, which was what we had originally. Okay, but additionally, the script that we ran at the very beginning saved these files not only as JPEGs, which we've been reading, but also many different files. There's a question in chat. Is the augmentation code adding the new samples or transforming the input sample? So it's transforming. I'm not quite sure what you mean by adding a new sample, but what we do is we select a specific index in the data set, which will always be the same. If you get the 50th index, it will still be, we'll say, or rather the 42nd index was a picture of corn that we already saw. And then it will randomly perform these augmentations. So maybe it gets flipped. It definitely gets normalized. It gets randomly resized and cropped in a certain way. The colors are changed in a certain way, and it's rotated in a random way. Same, all to the same image of corn. And then the big idea is that kind of remains, it's still a picture of corn, even though we've adjusted the pixel space in some way. And so it remains as the same class label and we can return it. When we call get item, yeah, so when we call get item, this is actually called when we say like data set of 42, directly calls get item with this being the index, if that's your question. Okay, continuing. So training with augmentation slowed us down. However, let's quickly explore, staving these in different methods. So we were originally looking at JPEG. Additionally, we'll look at PNG, NumPy, PyTorch, and that's all we'll explore for this case. I'll also mention H5 files are particularly useful when you're slicing your data in certain ways. So if you have maybe 3D scans or videos in particular, H5 files are particularly fast at kind of accessing that data. The worst possible thing you could do is save sort of a very, very long video as some file format that requires you to load the entire video at once in order to only get maybe 10 frames from the middle of it. Because that means every single time that you're trying to get those 10 frames, you have to reload the entire video. If you save that video as an H5, instead, you can just kind of select those frames since you know where those live in memory directly and you don't have to kind of compute them. Okay, so we'll evaluate all of these. What we'll do is we'll just loop over our data set 5 times, see how long it takes to load, and set a timer for it. Don't worry about the errors. That's with loading JPEGs. Everything still works. And what we see is, PyTorch, in this case, loads the fastest. And so once again, in the case that you're going to be training these models for a very long time, I encourage you to evaluate this, especially in the case that you can't do the thing that we're about to do, which is just load all of this in memory anyway. PNGs, unsurprisingly, load the slowest. The major reason for this is they also have the alpha channel, and we actually have to convert the alpha channel out. So just another operation that we're having to perform every single time is definitely going to slow it down. Great. So, I mean, even here, we can see that we can kind of get a significant increase in speed just from saving our files in different ways. But once again, nothing is free. We can see that while PyTorch is the fastest, it's also significantly larger than the other data types. So it's nearly 1 gigabyte, while, for example, the JPEGs, which are highly compressed, is only 15 megabytes. So if you have a very, very large data set, sometimes it is maybe necessary to sacrifice a little bit of training speed in order to be able to fit it all in a faster drive. For example, if you had a 2 terabyte hard drive, but only a 500 gigabyte SSD, you'll definitely see better performance placing this data on an SSD, but in a format that is slightly slower to load. Oh, that's later in the slides. Okay. But of course, some of you might have mentioned or might have thought, we're kind of slowly moving all of this into RAM anyway. Can we not just load all of it into RAM and select it from there? And the answer is yes. Of course, the way that we'll do this, we'll pick PyTorch files because we found that those were the fastest. First, we select all the files, just editing our init function and our get item function. And then we'll load the data. And so let's break down what this function is doing. So we say for each image in files, or for each path in the files, first we'll load the path in. So we'll load the image in, we'll convert it to a float, and we'll change the channels so that it's channels height width rather than height width channels, which of course, this is the format that PyTorch likes. Additionally, we can calculate the Y label here too. No reason not to, right? If we keep it in the get item, it's just sort of another part that's slower. So we'll move this same code just into some separate function, string to one hot encoding, split the string, get the index of the identity function, and return that value or return the class label. That goes here. And so this self.data just includes tuples of the image and the image's label, one after another. In the get item function, we get those two items, we augment the image, and we return it. In certain cases, you could even kind of perform some of these augmentations if there's maybe a discrete number. Like, for example, if there was only random horizontal flip, it could be quite efficient to just save both types of images. So save all of the images this way, save all of the images this way, double the length of your data set, since you have two of each type, and just return the index directly. That would be totally fine. Of course, in our case, some of these are random and to a point where we probably is not efficient just to copy 100 versions of the same image. And so instead we will perform these on the fly, which isn't too bad because remember, because of the data loader, this is happening asynchronously. Wonderful. So let's evaluate this once again. Only difference now being that we will also load this data in ahead of time. And we can see that this is marginally faster than the other approaches, maybe significantly faster than stuff like PNG, but a performance gain is a performance gain one way or another. Of course, I'll mention once again, nothing is for free. We're still taking up more memory in this case. So we're now loading our entire data set into memory. I'll take a moment just to mention one approach that you can do if your data set is too large to fit into memory is to load a certain portion of it into memory. This isn't always the most efficient approach, but sometimes it's worth it to evaluate. For example, if you can load maybe 3/4 of the data into memory, if you're training, you're loading these images asynchronously and training on them when they're loaded, often that can actually improve performance a significant amount. However, if you can only preload 5% of your data set into memory, it's probably more efficient to use the memory that you have in order to kind of have maybe a larger batch size, have more workers, a higher preload factor, something of that case. Wonderful. And let's now try to train with the preload. And we see that we get, 26 seconds. I was training on double the epoch time, which, isn't significantly faster than the other approach. So this one was about 28 seconds, but it is slightly faster. And of course, over the course of a day, a week, this is actually quite a significant difference. Not quite 10%, but almost 10%. So, these really can add up, these small changes. Of course, maybe it's not as drastic as the 1 minute and 8 seconds to 8 seconds that we went to earlier. But once again, we can see it's learning. Nothing kind of too special here. Okay, so we'll do a quick comparison. So kind of the naive approach took 1 minute and 8 seconds. We optimized the data loader just a little bit, and it went down almost by a factor of 10. We added image augmentations, and we found that this actually considerably slowed it down. And then we added preloading once again, and we got a slight increase in speed, which is handy. But let's take a peek at a couple of additional examples just to kind of get some extra practice with data sets. So we'll load in this next data set, which is the MNIST moving MNIST data set, which has 10,000 examples of 20 frames of two MNIST numbers slowly moving around the screen. So here's a quick example. We have a 2 and a 7. We can see the 7 is moving kind of towards the right, while the 2 is moving towards the left. So this is maybe a good task in image interpolation, a good data set for image prediction or future frame prediction. In our case, we'll say it's for future frame prediction, and we say we want to feed in 5 images and predict the 6th. Okay, so let's see how we would create a data loader for this. So first, we'll create our init function. One thing I encourage is sometimes you don't necessarily know what you'll need, and so you can build these later or add them on later. So we know the path. We can kind of put it directly here. If you wanted to put this as sort of a variable of the class as well, that would be fine. And so we'll load it in, we'll convert it to a torch tensor, and we'll permute the axes, just because I prefer samples, time, height, width. And additionally, we'll look at splitting the data set into train and test. Previously, we just had training. Of course, in actual approaches, we need a train and a test split. And so there's 2 ways to do this. You can do it outside of the data set using this torch utils data random split. And you actually give it this data set once it's instantiated, like here. And then you give it the length of the 2, train size, test size, and it will return you kind of subsets of those data sets that will work for that case. In the other case, you can actually do it within your data set itself, which we do here. We have this train parameter, which will be true or false. And we also have the split parameter, which says, what is the proportion of data that you want to split? So we'll get some index saying, this is the first 80%, maybe. So this is what we'll split to. Train data is up to that 80% index. Test data is from that 80% index on. Save the train variable and save clip size as well. The big idea of clip size is these videos might be 20 frames, but maybe we only want to look at 5 frames and predict the 6th. In that case, this clip size is something that we might want to vary. And so we'll have this as a parameter as well. We need to adjust our length function depending on if we're training. And then for the get item, we'll start at a random sequence within this index or at a random frame. We'll select the next, we'll say 5 frames. And then the 6th frame is going to be our target. Once again, if we're in training mode, we'll select from the training data set. If we're in testing mode, we'll select from the testing data set. And then we'll return these. Okay, we can instantiate our data set, say 80% should be training. This specific case is training, and we'll have a window size of 5. And we'll give it a quick example. So we'll just get the first example from the data set, and we'll view what we get. We get a tuple that has 2 elements. The first element being the X, the 5 frames that we input. And those look like this. And then the second element in the tuple is the label or the prediction, whatever we want to our model to predict in the end. And that's this. Wonderful. So that's working just fine. And in fact, we can say, okay, just real quick, let's benchmark it. This takes a little under 2 seconds to iterate through the entire data set, which isn't too bad. If you think about it, we're loading 64 by 64 by 6 for each item in the data set 3 times. And there's 10,000 items. So a pretty good ratio or pretty good efficiency there. Okay. So before we get on to the next data set type, let's do some quick overview of what we've discussed. Okay, so there's kind of a couple key components when it comes to creating fast data loaders and making sure we're loading in our data efficiently. And these are sort of some of the main questions that I think are quite important to ask yourself before we start to get kind of really into the weeds and into the very technical side of maybe we need to start building our own data loaders or things like that. So are we storing our data efficiently? So, if we're storing our images as a PNG and we have to perform this conversion every time, do we have the disk space to save these as a a PyTorch file, an H5 file, a NumPy array, or even just a JPEG? Are we storing our data in the best location? So when I was running this Jupyter Notebook edition, or at first on my own machine, I was actually storing my data on my hard drive, which was magnitude slower. I think even some of the optimized training runs would take something in the order of minutes, something like 4 or 5 minutes. So it's a really a massive difference. And in fact, we can kind of visualize this difference. You know, if some data is in RAM, it takes, we'll normalize to a clock cycle. It takes like 3 to 5 minutes to take, or, 70 nanoseconds. And if it's in an SSD, it takes an order of magnitude longer, 2 hours to 2 days. But of course, if it's on a hard drive, it takes another order of magnitude longer. So, 11 days to 4 months equivalently. So it really, really makes a massive difference where this data is being stored. Of course, the reason why we don't see preloading having a massive effect is because we're doing most of this asynchronously anyway. And so, we take away kind of a large factor of this. It takes maybe, 100 microseconds in order to perform a forward pass anyway. And during that time, we can load many images. Additionally, can we perform any pre-processing ahead of time? So if you have, it depends on whatever case you're doing. If you have some specific augmentations that you're doing every time, a recent project that I worked on, we had a camera and we needed to adjust the data in the camera. We had some overflow from the pixel sensors, or not overflow, but feedback. I can't remember the technical term right now. So basically we had to pass some constant convolution across the image every time. So, we have to do this for every single image, basically subtracting some neighbor's value from your value or from a value of a specific pixel. That's a great example of something that should be done ahead of time and then saved, in order to, just make sure that you don't have to do that every time, right? It's just kind of an unnecessary thing that is going to slow your process down. Only thing to kind of keep in mind here is sometimes the intermediate files can be quite large. So sometimes maybe you have to delete as you go and be kind of quite careful about not losing any data. And this is maybe a very significant thing is if you're working, and a more common one as well, if you're working with very high resolution images, but your model is not working with those high resolution images, right? If you have, 1080p and you're downsizing to 224 by 224, save it as an intermediate value. For many reasons, most critically being, it's going to take up way less IO, and you're going to be able to load, 16 images as fast as it would take to load one, which is going to, have a significant impact in your training speed. So specifically resizes, any operations that you're doing to any image, please perform, try to perform these ahead of time in order to save your computer some time. Additionally, with the data set, can we preload any of our data into RAM, or maybe all of our data into RAM? That's going to increase, our training time significantly, or decrease our training time significantly. Are we performing our data augmentations efficiently? And a key kind of example I'll give here is if you, for some reason, are, resizing in your augmentation, maybe you need to, which is totally fine. Often it's more efficient to resize to a lower resolution before you're performing other augmentations, right? I mean, most of these, if we go back to some of the augmentations we were performing, horizontal flip, normalize, random resize crop, color jitter, rotating, all of these are going to scale with the size of the image and how many pixels they are. And so if your image is 1/4 of the size, 1/8 of the size, 1/16 of the size, all of these are going to perform faster. So occasionally the order of these do matter. So keep that in mind. And then finally with the data loader, have you tuned the parameters? Generally, there's some good numbers, a batch size of 16, 32, 64, 2 to 8 data or number of workers, or however many cores you have on your machine is usually an okay number. Usually pinning memory should be true, but you don't always know. And it really does not take very long to test these things. And so, really, I highly encourage you, even if you're only gaining 5%, data loading speed, over the course of a day or a week, that becomes quite significant. You can save a significant amount of time for 2 minutes of experimentation. And then additionally, can we start to use some of these extensions? So torch.neuralnet.data parallel will split your data amongst multiple graphics cards if you have them. Even better, you can use torch.neuralnet.distributed data parallel, which improves upon this by, I believe, working a little bit more asynchronously across the GPUs. And so if you can extend your data loader or your model in this case to use these other methods, you're going to improve performance even more. This starts to get more into kind of the training side of things, but it's all sort of related to loading data in at the end. And then you can even further optimize by using other packages. So two that I'll mention in particular is Nvidia's Apex. I'm not quite sure what it stands for, but it has wonderful tools for, it has an improved version of distributed data parallel, which often performs sometimes magnitudes faster. It has mixed precision training, which can improve how fast you're loading in your data if you're storing it at a lower bit resolution by a considerable amount. Many frameworks like Detectron 2, which many models will use, will have these built in. And then also, you don't always have to build your own data loader or data set for that matter. PyTorch has a significant number of data sets built in already. And so we can see the TorchVision.datasets has a huge number. Syllabe, CFAR, Coco, Kitty, Kinetics 400, ImageNet. So, don't be afraid to just use one of these. They're quite useful. And they make you not have to worry about many things. So don't be too afraid to worry about these. It solves many of these problems of how do I load my data in quite efficiently. Another one I'll mention that I actually forgot is you can also, in certain cases, store your data as binary files, which can be even more efficient to load in certain cases because there's really no overhead or very little overhead. So there are some applications that I've done where that has been the most efficient thing. We were working with kind of very, very, very large images and many, many of them. And so it was more efficient to do that. Okay, so yeah, don't be afraid to use other packages as well. And then finally, we'll discuss kind of one last example for data loaders. And this is specifically in the case that potentially doing some random read on your data set is expensive, or your data lives more of a generative way, we'll say. And this is what we'll call, rather than map style data sets, iterative style data sets. And so how iterative style data sets work is instead of worrying about returning length and returning, the get item method, we still have our init method, but we now have the iter function. And so we actually return an iterator over our data. One thing to keep in mind that I'll mention very quickly is if you are using an iterable data set, this data set is cloned on each of the workers. And so if, for example, you're cloning this or you're working on this data one at a time, in this specific example, our iterator just returns a range from 0 to n. If we have many workers, each of these workers would be returning the same range. And obviously that's not quite efficient. And so instead, what we can do is kind of make sure that if we're in a worker process, that we're splitting up the workload accordingly. Sometimes this is a little bit more complex to do because sometimes these data sets aren't quite as cut and dry, but generally speaking, just try to split the workload evenly amongst the workers, and things will often be more efficient. Some specific examples of when this might be more efficient is, say, if you're streaming data from some source. You're not quite sure when it's going to get there, but at some point this iter will be ready, and the moment it is, you want it to kind of begin work on it. So that's kind of a specific case where this is better. In the case of some list, returning some range, this is actually not very efficient. So we see that if we do a single process, it takes like 3 milliseconds. And if we decide to spawn 8 workers to do it, it actually takes 100 milliseconds. The reason for this, once again, being spawning workers is expensive. While, actually returning range is not very expensive at all. So again, in certain cases, it can be more effective to have an iterable data set. Other things that I want to mention just very quickly is if your data set has a huge number of samples, shuffle is actually quite expensive. In every epoch it shuffles, so maybe that's not necessarily too difficult because epochs are relatively less common than just selecting a certain batch. But do keep that in mind. If your data set is hundreds of thousands or millions of items, a shuffle can take seconds occasionally. So just watch out for that. And that's actually most of what I want to discuss today. So if there's any questions, I'd be happy to talk about it more. I can talk more about loading data sets in general, the data loader kind of format. But the big picture is it's actually relatively straightforward. The init, the length, and the get item functions. I see there's a question. Samarth, do you want to unmute and ask?
Yeah, thanks. So the question I have is, when we are setting up the data loader, we specify these number of workers, right? So let's say our entire image repository has around 100 images, and we specify number of workers 10. Just hypothetical example.
Sure.
Then in one, let's say one shot, each of the workers will get 10 images from the repository. Now, is there any overlap in the data set of those 10 images that each of those workers have read, or they are disjoint?
Good question. So they would be disjoint. Basically, how it would work is your data set will become shuffled, and your 10 workers will get indexes 0 through 10, we'll say. This is if or 0 through 9, I should say. This is if your batch size is equal to 1. Keep in mind that if your batch size is 64, then the first worker will be getting indexes 0 to 63. Okay. So yeah, that's how that would work. They should not overlap. In fact, they should never overlap.
Yeah.
In the specific case that you kind of hit the end of an epoch and your batch isn't large enough, what happens is your batch simply isn't large enough. And so if your batch size is 64, but you only have 62 items left, your batch size will just be 62.
Oh, that's fine. So essentially, every worker will get a range of indexes. So let's say batch size is 2, worker 1 will get 0, 1, worker 2 will get 2, 3. So it splits the entire indexes of data into that range.
Yeah, just about. Of course, there are probably some like pseudo indexes because we've shuffled. But yeah, basically.
Exactly. So wouldn't shuffle also? I mean, so at the end of the day, they are disjoint. That's the main thing, because you don't want to leave out any data set from your training side. So because of this splitting across workers.
So I'm not quite sure the specifics of how they implement the shuffling, but one easy way to do it that probably their implementation is not far off is just create a permutation of the indexes. And then each data loader, if you get index 0 and 1, you're actually getting index 0 and 1 out of that permutation, which might be, data set index 417,000. Who knows? Okay. Someone asks, oh, sorry. Do you have you good?
Yeah. One more question quickly.
Sure.
I have used data loaders, and quite often the collate function parameter comes a lot into picture. So if you can talk about a little bit, when should we use collate, when it is recommended to use collate versus when it is okay to ignore it?
Sure. So, the big picture behind the collate function is you can, for lack of a better term, collate your lists into your different samples, right? Are you kind of discussing creating a custom collate function?
Yeah, custom collate. So what I learned is, if you look at your data loader get item function, it works only on one index. So sometimes performing an operation on an index level is expensive. But let's say if you have a collate function, it creates the batch, and then you perform it on the batch one shot. So that's what I know. But is there anything? What is the purpose of collate function or custom collate in general?
Yeah, so historically speaking, I've only used the collate function to kind of do custom batching. Like if there's a specific way I want to collect these batches, then I'll use the collate function for that. Additionally, if you have, here's maybe another good example, is if your first index, if you want to batch not necessarily only across the first index, this is kind of a more common case. So even I could have used this in the moving MNIST example. So rather than reshaping or permuting the axes, I could build a collate function that samples from the second index. Or even more specifically, I could build a collate function that samples some combination of the time and the samples, we'll say axes, right? And so basically it'll select some 5-frame window within that. And so I believe the way I've used it just to kind of extend functionality with how it's sampling if there's usually multiple dimensions or sampling from a dimension in a strange way or a unique way. Additionally, I think you can probably pad pretty easily with the collate function if you have like various.
Yeah.
That's probably a very common approach.
Yeah, in the text processing or natural language, we get the sequences and we have to pad sequences. So
yeah,
it's more efficient there.
Yeah, so I could see. I could see, one kind of very basic approach, or rather maybe not basic, but efficient approach would be, use this iterable data set on some, text file, read it line by line, and then use the collate function to pad each line to be, either 64 or 32 or whatever your context window is. And then if it's longer than that, you can, iterate over it, right? Just one basic approach, maybe.
Thanks.
I'm trying to think of anything else, but I can't think of anything off the top of my head. But yeah, good question.
Thanks.
There's a question in chat asking what's the major difference between a data loader and prefetching data. Okay, yeah, so at the end of the day, both things are kind of loading your data into memory. When you're prefetching data, let me pull it up. Okay, so when you're prefetching data, what we're doing is when we call this init function, we're automatically loading all of these images into RAM anyway. And so all of these images and their labels live within memory in this self.data array, obviously a pointer to it. And so when, we combine the two, for example, and we have a data loader and the self.data, really each process is only going to perform these augments. And that's all it needs to do, because after that, it's done. In the other case where we haven't preloaded the data, each process first needs to load this data into RAM. So it needs to call this torch.load on the image. Once it gets it into RAM, it can perform the augments and figure out the true label and whatnot. But at the end of the day, they are both kind of getting the final product ready in RAM to be moved to the GPU for compute. Of course, no worries. Good question.
So William, can you also comment something about, this case where we have very, very large number of small files? What would be the best way to store those and to access those?
Sure, great question. So one of the major issues if you have a ton of small files is your work. I mean, you kind of very quickly read a file and then move on to a different one. And this can kind of have a huge number of calls. And in fact, people have seen that just like the Python image library PIL, the open call has a huge number of kind of IO overhead, we'll call it. And so even though you're maybe not necessarily reading that much data, your process or your process will quickly become overrun and your computer kind of runs out of IO bandwidth. And so there's a couple different ways to approach it. If you have the ability, store as much as you can into memory, right? These are small files, so maybe that's an efficient way to do it. Otherwise, So it's a little bit interesting because in the specific case of having a large number of small files, you probably also have a small model. I mean, maybe not necessarily the case, but that does kind of mean you have less time to asynchronously load things. And so it can be a little bit difficult. One of the main things I would recommend is, I mean, all of the basic stuff first. Make sure you're, putting it on a SSD and, the most efficient SSD you have. Make sure that you're storing it in the best file type possible. And then beyond that, potentially explore combining these into maybe larger files. So you can randomly choose to kind of combine batches into a larger file, 100 of the same or 100 different examples in the same one, and select from that. Of course, you can kind of get some strangeness with your sampling since you're taking sort of a sample of a sample. So you have to be, wary about how you're performing that. But at the end of the day, that's just how you're implementing your get item function. So, I would say for the specific case of many small files, do all of the basic stuff first. And then if it's still kind of very bad, explore combining them into larger files.
So would using HDF5 format be helpful here?
Yeah, so you could store all of your, that's a great point, is you can store all of your small files into an H5 file because H5s are particularly beneficial when it comes to slicing. And so if you just need to get a specific index out of the H5 file, you can slice out a specific index of that small file, and it's quite efficient.
Yes. Do you have any sort of advice about what's the best practices for data loaders and for data storage on HAL in particular compared to other systems? Is there anything that makes HAL different in this regards?
Sure. I would say in HAL particularly, you often have access, or hopefully have access to multiple GPUs. And so utilizing data parallel and distributed data parallel are going to be even more significant, I'll mention. The IO is quite efficient. And so usually the bottleneck is going to end up being somewhere in augmentations. And so, making sure you're doing those efficiently, saving them as a smaller file size are all quite useful. Yeah, distributed data parallel is quite a useful tool. I encourage you also look at Nvidia's Apex. It has another version of distributed data parallel that I work with a lot that's quite efficient. And easy to work with too, which is always nice. But yeah, so specifically on HAL, using the parallelism across your GPUs is quite efficient. And then also you have quite a large amount of RAM. And so make sure you're preloading as much as you can, ideally. As well as the fact that you can kind of bump up the number of workers or the preload factor or the batch size, things like that. But that's about it. I mean, at the end of the day, it's still a computer. So nothing too crazy.
Okay, well, thank you for this insight.
Samarth, do you have a question?
Yeah, one more question. So like we have data loader in PyTorch, there are data loaders in TensorFlow as well. So, I mean, or equivalent data loader in TensorFlow. So computationally or performance wise, which ones are better? I've heard or even read there are TensorFlow is faster than PyTorch, so but it's more difficult. So any comments on whether if you have any idea about TensorFlow data loaders versus PyTorch data loaders?
Sure. So I believe TensorFlow data loaders have the slice. I'm not sure what they call it. I don't work in TensorFlow as much, but I know they sort of support slices more natively, which can be quite efficient. The thing that I'll mention is at the end of the day, they're actually probably doing very similar things under the hood. And with enough sort of customization, you'll be able to get equal performance out of either. So I'd say you'll get better performance out of the one that you're more comfortable writing in, because you'll more easily be able to kind of optimize and customize. Good question.
Okay.
I think that's actually an excellent point. Whichever tool you are more familiar with, you probably will be able to make a better use of it at the end of the day.
Yeah, I mean, PyTorch looks very easy to me in terms of making optimizations, but just was curious. Okay. And follow-up to this is, can we mix match the data loaders? Let's say create the data loader in PyTorch and use it in TensorFlow models for training and vice versa. Is there a possibility?
To be honest, I don't see why not. It's possible that there's some inefficiencies that might occur there. However, if at the end of the day, the PyTorch data set is just returning some data. And so if you decide to return these not as, torch tensors, but as, TensorFlow tensors, that's what they're called. I feel like there shouldn't be a huge issue. Yeah, I mean, it should be fine.
Okay, thanks.
Yeah.
If there are no other questions, William, thank you very much for such an excellent tutorial. This was very, very well on target, very focused and very detailed. So
Of course.
appreciate your effort in preparing and delivering this tutorial. So thank you very much for this. I think if there are no other questions, then perhaps we are done for today, and then we will see you next week.
Of course. Thanks everyone for coming. And may your data load quickly and your models train fast.
Yeah, that's a good wish.